Hello, and welcome to today's ACM SIGSOFT webinar. This webcast is part of ACM SIGSOFT's commitment to provide value to its current and future members. The ACM SIGSOFT webinar series features speakers from the Future of Software Engineering track at the International Conference of Software Engineering, as well as select keynote speakers and distinguished paper authors. My name is Sarah Gregory. I'm Senior Partner in the Intel Emergent Systems and Coaching team, and it's my pleasure to welcome you here today. Before we get started, I'd like to quickly mention a few housekeeping items that are shown on the slide in front of you. First, the slides will advance automatically throughout the event. On the bottom panel, you will find a number of additional widgets and resources. If you're experiencing problems with the slides or audio, press the F5 key in Windows, Command R if you're on a Mac, or refresh your browser on a mobile device. Or you can close and relaunch the presentation. To control your volume, adjust the master volume on your computer. At the end of our presentation, we'll have time for questions. Please type your question into the Q&A box at any time during the webinar and click the Submit button. This session is being recorded and will be archived. You will receive an automatic email notification when it becomes available. Today's presentation is Traceability is the New Black by Jane Cleland-Huang from DePaul University. Dr. Jane Cleland-Huang is Professor of Software Engineering in the School of Computing at DePaul University, Chicago, where she serves as the Director of the Systems and Requirements Engineering Center. She also serves as the North American Director of the International Center of Excellence for Software Traceability. Her research interests emphasize the application of machine learning and information retrieval methods to tackle large-scale software requirements problems. Dr. Cleland-Huang serves on the editorial board for the Requirements Engineering Journal and as Associate Editor for IEEE Transactions in Software Engineering and IEEE Software. She has been the recipient of the U.S. National Science Foundation Faculty Early Career Development Award, 4 ACM SIGSOFT Distinguished Paper Awards, and 2006 IFIP TC2 Manfred Paul Award for Excellence in Software, Theory and Practice. She is a member of the IEEE Computer Society and the IEEE Women in Engineering. She's a frequent collaborator with industrial and governmental partners, including Tata Consultancy Services, Siemens Corporation, and the U.S. Food and Drug Administration. Dr. Cleland-Huang received her PhD in computer science from the University of Illinois at Chicago. And Jane, we look forward to your presentation today. Let's begin.
Thank you. Okay, so in this webinar, I want to discuss some of the benefits that we can realize from incorporating traceability as an integral part of the software development process. So traceability is perceived by many people as a necessary burden upon a project, inflicted probably by process improvement initiatives or so that we can have our software approved or certified if it's in the safety critical domain. But today, I hope that we can take a new look at traceability and explore some of the ways in which it provides fundamental support for delivering project intelligence. Because I'm not really sure that I can convince you at the beginning of my talk that traceability is the new black, I'm going to have a working title, which is Software Project Intelligence, and we're going to first of all look at that. So everybody is familiar with the notion or the concept of business intelligence. So business intelligence takes the organizational data, it performs data mining and analytical processing, massages the data and presents it in the form of information that helps us to improve our decision-making process. But in this talk, I want to coin the term project intelligence. So instead of business intelligence, look at project intelligence and apply the same practices that we apply at the business level to the data that's produced as a byproduct of the software development lifecycle. So project data, as we're all aware, is made up of many different parts. We have regulatory codes, user requirements, stakeholders' requests, all sorts of different requirements from system level down to component subsystem level requirements. We have source code, documentation, change requests. We have all sorts of project management and tracking information, and we have fault logs. So the project data that is available to us is very diverse, and this is the data that we would like to use and integrate into our project intelligence. But there are also a number of challenges. So this data tends to be distributed geographically, sometimes behind different firewalls in different parts of our organization, or even across organizational firewalls. The data is in very different formats. So we have heterogeneous data. For example, requirements might be stored in a requirements management tool, such as DOORS, and design documents might be in tools such as Enterprise Architect or ePro. So all of the data is stored in these different formats, and the idea or the notion of extracting it and manipulating it and using it for project intelligence means that we overcome the difficulties and the barriers that are inherent to this kind of distribution in these different formats. So we therefore have to also solve the challenge of data connectivity. It's not just a matter of accessing the data, retrieving the data, but we have to actually connect the different artifacts in meaningful ways. And data connectivity is what we have traditionally referred to as traceability, when we look at relationships between requirements and code or between regulatory codes and requirements. We also have to provide support for software analytics. So once we get all the data and we bring it into one place and we can make connections between artifacts, how do we analyze it? What are the things that we can do with our data that would bring us real project intelligence? And finally, even if we have these software analytics in place, we've found in our experience that it's a real barrier, the difficulty of actually retrieving that data and issuing queries against it. So in this talk, I want to focus on three primary areas. First of all, briefly on how we actually connect the data. How do we retrieve it? And then in more depth on how do we establish traceability between the different artifacts so that we can support the kind of project intelligence that we're after. Secondly, what are these software analytics that we would like to integrate into our query mechanisms? And third, how do we overcome this barrier of the difficulty that stakeholders, project stakeholders have in actually accessing the data and using it in useful ways? So we would like to deliver project intelligence, and I think we can see that software data could be used strategically if we can overcome these barriers to deliver meaningful project intelligence and to answer queries that are important to us. So the goals of this webinar are, first of all, to suggest or pose some strategic questions that we would like to be able to address, identify some kind of analytic queries that would deliver real critical project intelligence, briefly talk about how to instrument our development environment to support all of these things, and along the way I'm going to discuss a couple of cutting-edge research areas that are helping to enable some of the challenges that I just mentioned. And finally, I hope that by the end of the talk, everybody will be ready and willing to embrace traceability as the new black. So first of all, let's take a look at what kind of queries we might like to ask that really constitute, that will provide the data that we need in order to gain this project intelligence. So I'm going to give a few examples of these. In the area of regulatory code, we may want to ask questions such as which regulatory codes are relevant to my system. So we have regulatory codes, we have requirements, code test cases, and we want to know which of all the thousands of regulatory codes in some systems engineering projects impact our system. And are these codes being fully addressed in the as-built system? And a question that is usually pertinent is, how do changes in the updated regulatory codes as modifications and new revisions come out year after year impact my as-is system? So if you bear with me, I understand that answering some of these questions can be difficult right now, but we want to think about what we would like to be able to have our project data do for us. In the area of project test status, we could ask basic questions, which we can probably answer today. What percentage of acceptance tests have passed? We also want to ask more analytical questions, like should we invest further time testing? Do any of the reused components have histories of post-release defaults? And such questions. In another area of bug triage and fixing, we might want to ask questions such as what's the history of changes for this component, or a more analytical question, like who should we assign this bug to? Or are any new fault trends emerging that we haven't previously seen? And I hope what you can see from these sample of questions is that some of them can be answered quite simply based on raw data that we have collected as a byproduct of our project, but some of them are more analytical in nature, and we would like to have mechanisms in place that we can integrate all of these things together. So here's a couple more examples for the project management. For example, how did the recent process change impact the delivery stream? So lots of questions, but what is really important here is that each person thinks about their own organization and their own project and what kind of questions will be pertinent for them to answer. So if you wanted to benefit from project intelligence, what would you want to know? What kind of questions would you like your data to be able to answer for you, or to give you the information that you need in order to answer those questions? So we're going to take a closer look at the challenges. And as I mentioned, we're going to look first of all at how we retrieve and connect data, and then we're going to take a look at software analytics and then querying the data. So first of all, in the area of accessing and integrating data, I've worked on several projects in this area. One of the projects I worked on with my industrial collaborators was a mechatronics traceability project, and the idea was that we would be able to have enterprise-level traceability, so that if you are sitting inside a tool, for example, inside Eclipse or inside Enterprise Architect, you could issue a query, and data would go and be retrieved from inside other tools that could be geographically distributed and also stored in other different kinds of formats, and that data could be synthesized and used to answer the question at my point of need within the tool I was currently working in. So I might ask a question if I had Enterprise Architect open, I was looking at a component, I might ask which requirements are relevant for this component and which regulatory codes do those requirements address. However, one of the difficulties of creating these kind of gateways or adapters into these heterogeneous tool sets is the difficulty in maintaining them when the tools change. And so I'm not going to talk much about that today. It's not very difficult to build adapters to access the tools if we want to do that, but it also probably makes sense to invest in some kind of service that does this for you. So for example, TaskTop, which is a company out of Vancouver, they provide this service as their business for integrating different data streams and integrating the process so that you can have all the data available to you. So I'm not going to say more about that. Secondly, the next challenge is knowing what you want. And you see I have a pile of coins up in the top right-hand corner here, and that's to remind us that we need to answer these questions in order to understand, to make a business case that clarifies to us the return on investment of the cost of collecting and managing the data that we need in order to support the project intelligence that we're interested in. So the first thing we do is we create what we call a traceability information model. So this is basically a database schema of the software artifacts or the engineering artifacts that you have in your project. And I tend to use the word software artifacts, but like I said in the project on mechatronics traceability, many of the artifacts we wanted to trace into and query were basically mechatronics components that modeled the mechanics or the electronics of the system. So we represent our artifacts. You can see preliminary hazards, system requirements. This is a small subset of artifacts you're likely to have in a project, and obviously I've reduced it just so that I can illustrate it on a screen. We also decide which of the attributes of those artifacts we want to expose for query purposes, and we establish conceptual traceability paths between these artifacts. So these are the places that we would like to establish direct relationships. For example, specify a set of mitigating requirements that mitigate specific preliminary hazards. So now we can take the queries that we have just posed, so the questions we would like our project data to answer, we can map them onto this data schema, the schema of our project, and we have to ask a number of questions. What really refers to the questions, like what kind of questions do we want to answer? Why do we want to answer them? So what value will it bring to us if we collect the data in order to answer these questions? How are we going to collect the data? Who is going to collect it? Oftentimes with traceability, the effort of collecting the data is exerted by someone that is not the beneficiary of it. So we need to understand this. Who's actually going to use it, and when is it going to be used? These are important questions. I've visited a number of organizations, and on one occasion, the software developers told me that they had very extensive traceability in place, but they didn't actually know how to leverage the trace links and how to query it to support anything useful in their project. So we have to ask these questions as part of the planning process. Okay, so let's say we have answered those questions. We know what kind of queries we want to issue. We now have to establish traceability that will enable us to connect artifacts together. So I've talked quite a bit about traceability in this talk already without giving a proper definition of it, and the Center of Excellence for Software Traceability provides this definition: the ability to interrelate or connect identifiable software artifacts with each other, to maintain those links over time, and then to use the resulting network to actually answer questions and about the product and the process, and of course that's what we are concerned with today. And you can see the kind of traditional uses of traceability shown on the right-hand side here, but my message today is that traceability can support very focused, very analytical queries instead of just retrieving artifacts for us. So we need to connect the artifacts, and there's actually 4 different ways that we can go about accomplishing this. You'll see at the bottom: manual, dynamic, project exhaust, and process driven. So I'm going to touch on each one of those, and in the area of dynamic generation, I'm going to give a few examples of some current cutting-edge research which is going on in that area. So first, I would like to quickly mention that we have a traceability problem. We performed a study in conjunction with the Food and Drug Administration looking at the traceability components in the submissions for medical devices to get their approval for marketing. And we found that tracing problems are inherent to these submissions. So these are some of the problems that we identified: a lack of planning. I've already discussed the importance of that. Ill-defined trace granularity, so it looks as if the trace links are very ad hoc. Redundant trace paths, missing links, and basically traceability is an afterthought, and that seems to be a recurring theme. Build the software, and then at the last minute, create the trace links for the approval or certifying process. But the problem with that is that we miss all the benefit of having the trace links throughout the development process, and I hope I can persuade you that it is worth changing the way we go about this. Just to show you another example of what we have termed the traceability gap, this is basically a model of some of the artifacts and the trace links that are prescribed by DO 178B in the aeronautics industry for certifying software. And this is a parallel model of an actual software implementation that comes under that certification, and you can see all of the problems: the missing trace path, missing links, incompleteness. So getting complete and accurate traceability is very difficult, and we need to be strategic about it so it actually brings a return on investment for us. So I mentioned that there's 4 ways that we could go about creating trace links. The status quo basically uses manual link creation. I'm not going to talk much about this except to say that it can be very difficult, even if we use tools such as Jaws, which is a requirements management system, and use their drag and drop features. It can be very difficult to maintain trace links in an accurate state when the system starts to evolve. And as a result, people tend to not completely trust their traceability matrices. There's a number of techniques that use what we call just-in-time traceability. So these leverage information retrieval. You can see two tools, one that we developed at DePaul called Poro, and the other is Retro, which came out of the University of Kentucky. Both of these techniques use information retrieval to try and identify similar components. So in the top left, you can see we have a regulatory code. We perform an information retrieval search against a set of requirements, and the ones that are most likely to be linked are retrieved. So this kind of technique is very helpful for augmenting manual approaches. But it has a flaw that it's limited according to what we refer to as the term mismatch problem. So the term mismatch means that, of course, there's going to be cases where there are no terms in common between two artifacts, perhaps a regulatory code and a requirement, or perhaps a requirement and a piece of source code. There's no terms in common, and so the automated trace link fails. So I want to talk a little bit about some of the cutting edge work that's going on in this area. And we're working on a project that's moving towards more intelligent traceability. And the question here that we asked a few years ago is, what goes through a domain expert's mind as she performs the tracing task? So we know humans can look at two artifacts, use their domain knowledge, and determine whether those two things are linked or not. So we're moving this work in information retrieval into this kind of higher level. So here's an example. We have a regulatory code, and then we have a requirement. The regulatory code starts with the status of field elements, and then the requirement is the second one, the highway wayside segment. And we wanted to think about how a human would actually perform this trace. One of the things you'll notice is there's very little in common in terms of terms between both of these artifacts. But a human performing the trace would know that WIU stands for Wayside Interface Unit, and it's located inside the highway wayside segment. He would also know that broadcast and transmit are similar in meaning, that the automobile controller is part of the automobile, that WSM and wayside status message are equivalent, and he would be able to reason about all of these and understand that both of these sentences involve highway wayside segments sending status messages to automobiles. And because he can reason about this, he would determine that trace links exist. And I'll mention here, I'm focusing my examples on between regulatory codes and requirements, but many people have done the same work in the area of tracing requirements to design or requirements to code. And what we find is that source code is very rich with comments and meaningful variable names and class names, which means that tracing to source code is just as effective as tracing to textual documents like requirements. So I don't have time to explain exactly how this more intelligent traceability model works in detail, but I'll mention that there's three major concepts. The first is an action frame. So we can use natural language processing to represent each of the artifacts as an action frame. We have a domain ontology, which contains the concepts of the domain, and then a set of link heuristics, which reasons about the action frames in the domain ontology and the concepts in the various artifacts, and reasons about them and determines when a trace link can exist. So very briefly, we have two artifacts here. We want to know if they're linked together. We process them using natural language processing, extract the action frames, and you can see the action frame here. It's labeled actions, semantic groups, recipients, themes. And then on the right-hand side, we apply a set of link heuristics and check them against the action frames. If the heuristics pass their test, then we can determine that a link exists. So this is a kind of upcoming area where I think we're going to see some good breakthroughs in the way we can actually achieve traceability, automated tracing in practice. And you can see in the graph in the bottom left, the highlighted or the circled results show the results that we obtained in one project we conducted with positive train control requirements and regulatory codes. And you can see that we're moving results up to a place where we're getting both high recall, and high precision, which is exactly where we want to go with these automated approaches. Okay, back to the third method. So we've looked at manual traceability, we've looked at automated approaches. There are some other approaches which can be incredibly effective. This first one is leveraging project exhaust, and I'll give one example of that. When source code changes are committed to the repository, if we tag the simple commit, so with references to test cases and requirements, then we capture the fact that this code is related to this requirement and to this test case. And for very little effort, we actually establish traceability. So if we were to start such practices in our projects, then we would have the traceability in place that we need to deliver the project intelligence that we are after. And in a closely related area, probably the most effective way of generating trace links is to build the practice into the process. And I think the best example of this is some of the agile tools where you may specify user stories, break the user stories down into tasks, assign test cases to those tasks, and basically as part of the agile tool, all of these things get related together as you're going through the process. And everything is maintained because it's part of the process by which you go about coding and evolving your software. So if we can adopt some of these process-generated trace link generation practices, then we're going to have at our fingertips the traceability information we need in order to answer the kind of queries we want to answer. Okay, before I leave this notion of creating trace links, I want to just very briefly mention that it's also very important to evolve them, especially if we're using automated methods or manual methods. And this is one example of an ongoing project. And in this project that's conducted by my PhD student, Mona Rahimi, the starting point is a set of requirements and a set of source code. So in this particular project, we're looking at evolving links between requirements and source code, but we could apply this to other pairs of artifacts. So we start off with requirements, source code, and trace links. So this would mimic the scenario in which you have developed an extensive set of trace links, which you have submitted. If you're building a safety critical product, you've submitted it as part of your submission for approval or certification. Your product is approved, it goes on the market, and then over time you evolve it and you make changes. The requirements change, the source code changes, but more often than not, the trace links are not evolved accordingly. And in this particular project, we can do things like use natural language processing techniques to detect changes in requirements and changes in source code, and use structural analysis, for example, refactoring detection tools, to identify changes in the source code, and then we can apply we can test for a set of properties to see if they exist and apply, again, link heuristics to evolve trace links. And you can see the results in the top right-hand corner, which show that if we put this kind of infrastructure in place, the red dots are represent the trace links or the quality of the trace links following this process that evolves trace links, while the blue diamonds represent the quality of the trace links if we have to start from scratch when we submit our second version of the software. So evolving trace links is of great importance. Okay, so let's assume at this point that we have decided we would like our project data to answer queries for us, and we have determined how we're going to instrument our environment so that we have the ability to connect the data together so that it can support these kind of queries. As I mentioned previously, accessing the data and issuing queries against the data can be extremely challenging, and so I want to take a look at that. So here's an example about why it's challenging. Let's imagine we have this query in the top left. It says return code classes associated with high-risk preliminary hazards which have failed test cases in the past month. A very simple query. it's actually not even including any analytical function. It's just asking us to manipulate and retrieve the raw project data. If you look at the traceability information model, I've already colored the artifacts or the classes that we need to include in our query. So the query mentions preliminary hazards, test cases, and test case results. And of course, our query has to traverse all of the software artifacts that create the connections between those things. Not only that, but what's hidden from view here are all the trace matrices that are in between them. So basically what this means is if we were to issue such a query using SQL, that we would have to issue that query across 11 different tables. So it already starts to get a bit messy. Furthermore, we have to put some constraints on the query, and then we have to specify exactly which attributes we want to retrieve. And a few years ago, I found this call for help, which is shown on the right-hand side of this screen, on one of the open forums. And you can see somebody was trying to, they called the subject Traceability Query, and they're saying, I have the following query, and it has all of that SQL in it, and it gives me the aggregate number of test cases, etc. What I need is the aggregate number of test cases linked to each requirement. Help, can anyone help me? And our experience is that the kinds of queries that are useful for supporting software engineering or to give us this kind of project intelligence are actually quite challenging for people to formulate. And so they need help with that. So what solutions exist? Well, 3 solutions here. First of all, we could provide some kind of structured way of helping people, like a query builder, to help people compose their SQL queries. And I'm using the term SQL here, but it's really a kind of stand-in for a structured query mechanism. So, for example, if the data is distributed, you're going to have to formulate your query in a structured way, and then interpret that query in such a way that it can go and retrieve data from the distributed nodes and then reintegrate the data. But I'm focusing right now on the barrier part of it, the first barrier, which is to actually formulate the queries in the first place. In the top right, you can see visual queries. So this is actually, this example shows the visual trace modeling language. And VTML basically allows us to model trace queries over the database schema or over the traceability information model. So this is a UML profile, and what we found is that people find it much easier to model queries and to understand queries this way in a visual way than to actually write the SQL. Or we could support issuing of queries using natural language. So in this case, the person just says, give me a list of all Java classes, etc., associated with high-risk preliminary hazards, and he doesn't need to worry about how that gets translated into the SQL. So is that a pipe dream or not? Well, the first thing I did was to go and ask Jeeves. So the text here is a little bit small, but basically I asked Jeeves what percentage of acceptance tests have passed. That's about as simple a question as we could ask. And Jeeves, of course, returns all sorts of generic answers about test-driven development, metrics for acceptance testing. So he can't actually answer my question about a specific project. What about Siri? Well, I asked Siri the same question, and Siri also returned similar kinds of things, an article about acceptance testing, and for good luck, she threw in something about drug testing for welfare recipients and public assistance. So Siri wasn't much help either. Well, for a little bit more Siri fun, I asked Siri, who is a domain expert for this problematic component? And I got an article on subject matter expertise and expert systems. And finally, do any of the reused components have a history of post-release faults? To which Siri answered, interesting question. Okay, I'm sure you're thinking, well, that's not fair. Siri is not designed to answer those kind of questions. And that's exactly my point here. Siri can answer very well a very broad swathe of general knowledge questions, but it's not designed to answer specific questions about our project. So we need a tool or a mechanism that can do that. I'm going to talk a little bit about one of our recent projects we call Ticky. And Ticky is kind of like a play on Siri, but it has trace queries, TQ, in the middle of it. And the goal of Ticky is to take either a spoken or a written query and to generate SQL from it. Now, we have goals that go far beyond generating SQL, but that's what I'm going to talk about today. So Ticky is designed to answer questions such as, are there any hazards with no identified contributing faults? List all tests which have recently failed and which are associated with high severity faults. And I'll say we have trained Ticky based on a large collection of queries that we've collected from a variety of software engineers. Then there's other kinds of questions such as, is the system safe for use? Well, that's a little bit higher level, a little bit harder for Ticky to actually answer such a question. And obviously we have to have some intermediate constructs in place that would transform that into something that Ticky could actually implement. And finally, questions like, what's up, dude? And, you know, obviously Ticky's never going to be able to answer every question that gets asked, but we would like her to be able to answer project-specific questions. If you're curious about how this works, we take the initial query, we pre-process the query into some basic formats. So for example, taking I'd like to see a list of all and just replacing that with the word list. So we simplify, we tokenize, and we map the tokens onto the project. So specifically, we map these tokens onto a table name, onto an attribute name, or onto some data that is found in one of the artifacts. When ambiguities exist, we apply a set of heuristics. We have heuristics, and we're focusing on some machine learning techniques that identify the most likely query. And here you can just see a mock-up of the Ticky screen. We return back to the user the SQL, and we actually nowadays have improved this by eliminating the trace matrices so that they are just hidden from the user. They don't complicate the picture. The VTML query, because some people prefer the visual and some prefer the SQL, and then the query output. So the user can basically say, show me your software requirements realized in UML classes, etc., and get the response back again. And we're currently working on some techniques that will allow the user to interact with this result and to disambiguate when ambiguities exist. Okay, so Ticky can help us formulate queries. And I should mention that Ticky is a work in progress. We're going to release Ticky in about 4 weeks for general public to try out. It's hosted as an ASP.NET web service, but it's not perfect yet, and Ticky's still learning how to answer some of the questions. But I'd like to look at some of the different kinds of data that we might be interested in. So the first one here, we ask to, for example, to retrieval requirements with open issues. So this is very basic. We're just querying the data to get the basic information back for us. So currently, this is actually a problem for some people because they don't have good query mechanisms in place. The next two are related. So the first one is synthesized data. So that's taking data that exists in the system and merging and synthesizing it in new ways. And the third one is actually producing new data. So for example, predict which safety critical components are likely to exhibit future bugs. So this falls under the area of software analytics, which is where we're interested in, which is what we need to support in order to be able to actually answer analytical queries. So now in this example, I've taken the traceability information model. You can see we have the artifact name or the class name at the top. Then we have attributes, And then we've added this extra bit at the bottom, which appears in the kind of operations section of the classes in this class diagram, and represents operations that we would like to perform on the data. So I'm going to, so you can see, for example, topics. So this means on hazards, we would like to be able to perform topic analysis. And we would like to be able to answer questions that relate to hazards of a specific topic. Hazards related to the mechanical arm, or hazards related to temperature controls in an isolate system, a baby isolate system, incubator. We would like to be able to perform trending operations on the faults, so to predict specific trends. We'd like to be able to perform find the expert, so to answer questions like, who is the subject matter expert? Or here in the bug tracker, who is the best person to be assigned this bug, to fix this bug? So now we go back to the initial part of this talk where I asked you to think about queries that you would like to ask. Some of those queries, if you have been imaginative, will include software analytics. Some of them will be basic ones that will just include retrieving data. But we want to be able to do more than just retrieve data. We want to be able to perform these software analytic functions. So two specific examples, which you can see illustrated here, is the bug hunter, which is basically the fault-prone approach, and then find the expert. So these are two examples for which we've actually built prototypes, and I'm going to talk briefly about those. This is actually current work, so I don't have many slides for it yet. But let's say we wanted to integrate into our project intelligence and our query mechanism the notion of fault prediction. We would like to be able to answer queries such as which hazards have been implemented in potentially buggy, or which hazards have been mitigated through requirements implemented in potentially buggy areas of the code or potentially fault-prone areas of the code. So we want to build a function that can support that bug prediction, and we want to integrate it into our query mechanism. So the first thing we have to do is to think about what features we need in order to support this analytical function. So if we're talking about fault prediction, then obviously we need to have some ability to analyze the code. For example, there are tools like Jayhawk metrics, which can be run within a couple of seconds through quite large source bases, analyze the coupling and complexity metrics of your object-oriented code. So those will be considered possible features for including in the analytical function. Once we get these scores back that are returned from the metrics computation, then we need to have other features. We could, for example, use machine learning and have an analytical, build a classifier that uses those metrics to differentiate between potentially buggy and non-buggy code. We could use other kinds of metrics, for example, social metrics. We could use statistical regression models. So the idea is you think about the analytical function, you model the features and the valid compositions. If you want to actually integrate this into your project intelligence infrastructure, then you need to implement the chosen components as chosen features as components, and then configure an analytical function. So an analytical function is going to be something called predict faults. It's going to include some composition of these features, and we're going to then have to train it on our own project data. So a lot of these analytical functions, when you get into these areas of machine learning and data mining, they work far better when you've had the opportunity to fine-tune them and test them and to retrain them on your own data. So we're going to configure these analytical functions and then instrument the query environment to support the analytical functions. And then we can make a decision. The easiest way is, once we have these functions, is just to run them in batch mode overnight. And produce the data, and then we have that data available to us in the traceability information model just as a regular part of the query process. One of the problems with this is that certain class of analytical functions become stale. The data that they produce becomes stale very, very quickly. So for example, if you were to create an analytical function which evaluated code for bad smells, and you were to run that overnight and then send that to your developers in the morning, then the chances are that the things that were bad smells yesterday may have been fixed overnight, or fixed at the end of the day, or fixed early in the morning, and they're not particularly helpful to the developers. So we have to make sure that the data is generated in a way that is sufficiently timely for the analytics task it's producing. So we can either run this as a batch function, or we can create it as a user-defined function and integrate it dynamically into our query mechanism. Of course, it's going to take longer to run that way, but it's completely viable to do that. So finally, we've equipped our project now to actually answer these analytical queries. So we have our traceability information model, we have our analytic functions defined and implemented, and now we can ask a question such as, who is the best person to check the fault-prone classes in components related to temperature controls? So you may notice 3 different analytical functions here. Who is the analytical function that's looking for the domain expert, then we have the fault prediction, and then we have the topic modeling. But we've been able to integrate this into our query mechanism, and whether you integrate it into a Ticky like natural language solution or a more structured query mechanism, it doesn't really make any difference because this data is treated, these analytical functions can be treated just as data. So what are the next steps? Okay, what I hope you're going to take away from this webinar is if you want to support project intelligence in your project, the first place to start is to think carefully about the queries that you would like to be able to answer. Next step is to identify the relevant artifacts. So map those queries onto this traceability information model and make the determinations about who, what, when, why, etc. And then build this model as a strategic plan. So you need to decide, based on your questions, how you're actually going to collect the data that you need and when you're going to establish traceability links between them. Instrument the environment accordingly, according to your decisions. Connect your data. So as previously mentioned, there's a variety of ways to do this. You can maybe just connect your data because you're using an integrated development environment, in which case your data is going to be connected to start with, or you can use some external tool or service or build that infrastructure yourself. And then finally, design useful analytical functions that you can integrate into the queries that you want to ask. So in closing, I'm going to return to my claim that traceability is the new black and ask why is it the new black? Well, the cost of connecting artifacts, the cost of tracing things continues to decrease as we move more into these integrated development environments where traceability is established as a byproduct of the software development process. And as our ability to dynamically generate these trace links continually grows and advances, and the cost of generating or collecting accurate trace links and maintaining them certainly decreases. Project intelligence in the form of these kinds of queries that we've talked about today is going to deliver real value to our project if we just strategically consider which kind of questions we would like to ask. And finally, traceability is fundamental to empowering project intelligence. And just in closing, I would like to claim the new title of Traceability is the New Black. And if anybody's interested in seeing more about Ticky, we will be releasing it soon, and we will be posting information as we release it on our coest.org website. Thank you.
Okay, thank you, Professor Cleland-Huang. We've had a couple of questions that came in and just a few minutes available to take those, but let's start with the first one, which was posted right around slide 28. The natural language processing that you see being used, for example, for information retrieval purposes, I assume it tends to be corpus-based techniques, since technical documents tend to be idiomatic and or full of jargon, noun phrases, etc. Would that be the case?
Is there any clarification about what corpus? I'm trying to look for the actual question. Can you clarify what is meant by corpus-based?
I'm not sure if the questioner is on.
Okay. Okay, so
From
let me
the
just address this in a kind of general way, and I see the question now. Let me open it up here. Okay. So certainly the technical documents are filled with idioms and jargon. And I think that's one of the reasons that it's incredibly important to understand the vocabulary of the domain that you're working in, and not only the vocabulary of the domain, but the vocabulary of the organization. So we need to, first and foremost, start with a project glossary. So a lot of the terminology used in each individual project can be defined in the project glossary, and that can be fed into the natural language processing. And then this whole kind of notion of having a domain knowledge base, which I believe is what we're kind of referring to, the questioner is referring to in this idea of corpus-based techniques, is that we need to learn the terminology for a specific domain. So this is challenging. It goes into the area of ontology building, and so a lot of the things that I've actually talked about in terms of intelligent traceability is really relies on the notion that you do understand the terminology, and you've captured it and represented it in a knowledge base or in an ontology for that domain and for that organization. So yes, this information does need to be captured.
Okay.
And okay, I see that David has kind of clarified use of documents to train the natural language processing techniques used. Absolutely. All of the techniques that I presented here today all require training. And one of the things that obviously we need to look at is once you've trained some kind of tool to perform these tasks, then how applicable is it to documents in other domains? And we've looked at this to some extent, but there's obviously a lot of work that still needs to be done in that area.
Okay, thank you. Do you think it could be interesting to use data visualization to answer the questions that you talked about?
Okay, so that's a really interesting question from Gilberto. And I think the answer is definitely yes. So I think ideally we would like to, instead of having a standalone traceability /query tool, we would like to be able to integrate the querying and the response to the queries into a more kind of natural environment. And some queries lend themselves to visualization. So I think this would have to be kind of customized according to the specific question. One of the things we've talked about before is not just issuing the query and getting the raw answer, but in understanding what is the best way to actually represent answers of this genre of questions. So I think that's a great question, and absolutely an open area of research that we need to learn a lot more about how we visualize data that answers some of these different kinds of questions.
Okay, thank you. And that probably relates then to another question that Dave asked. In addition to better querying for information, he notes what's also sadly missing is some sensible browsing of information, for example, graphically based on classification type information. So it's, again, visual representations.
Yes, I think, so the question of, browsing versus search is always an important one when you talk about any kind of information retrieval. So browsing, of course, also requires the traceability that I was talking about in this particular webinar, because you want to be able to browse collections of artifacts. So some tasks are definitely set up better for browsing. And also, even if we issue a query and the query is not able, because we're using information retrieval techniques, and if we're not able to return results in a way that's 100% accurate, then basically we need to present the results to the user in browsable form. The benefit, though, so they still have to browse for the answer when this is when this scenario arises, but the benefits of this are that the amount of space, the search space that they have to look through is significantly reduced. So let's say we had 1,000 documents, but in many cases it's many more times more than 1,000, and we're able to reduce the search space for them to 1% or to 10 documents, and then they browse through those 10. Then I think this is a really good combination of browsing and search.
Okay, thank you. Well, I'm afraid we've run out of time today. As you know, a couple of questions just came in, but we are right up at the top of the hour. I'd like to thank Professor Cleland-Huang again for her informative presentation and for insightful answers to the questions that have been posed that we were able to take. Also, special thanks to each of you for taking the time to attend and participate in today's webcast. This webinar was recorded and will be available online in a few days at www.sigsoft.org/resources/webinars.html. You can find announcements on upcoming ACM and SIGSOFT webinars and other ACM activities at learning.acm.org and www.sigsoft.org. This is Sarah Gregory from Intel Corporation, and I'm saying goodbye for now. Thanks again for joining us today, and I hope you'll join us for another ACM webinar sometime in the future. Thank you.